Welcome back to our video series on the Adaptive Fisheries Assessment and Management Toolkit. We're now going to talk in detail about Step 3 of AFAM, which is selecting performance indicators and reference points. I really like this quote by Yogi Berra: "If you don't know where you're going, you'll wind up someplace else." So this step is all about thinking about where you want to go and how you're going to measure your progress towards that goal. Here's a roadmap for this session. So in the presentation, we're going to go over some definitions again to go over what are performance indicators and reference points. I'm going to give a bit of background on fish life history information. So this is information on the biology of fish and how this helps us determine how healthy a fishery population is doing. Then I'm going to go over the details and theories of all of the indicators included in the toolkit. Finally, we'll have an activity where, using AFAM, you'll select performance indicators and reference points for your fishery. So here's a bit of a refresher from the overview presentation. Performance indicators provide information about the current performance of the stock. They indicate how things are going. So, example performance indicator might be how many fish in the catch are mature. A target reference point is a value that indicates that the performance of the stock is at a desirable level. So this is a place you want to shoot for. This is your target. So for example, if the fraction of fish in your catch that are mature is your performance indicator, the target reference point might be 90%. A limit reference point is a value that indicates that things are not doing well. This is an unacceptable state of the fishery, for example, if it's highly overfished. So in AFAM, we'll select one or several performance indicators, and for each of these, we'll select a target reference point and a limit reference point. Again, no single clue is perfect. No data-limited assessment method will tell you exactly how the fishery is doing. They each will tell you a little piece of how the fishery is doing, a snapshot of how it's doing from a different angle. So in this picture of an elephant I really like to show, if you were a miniature person looking at it from different angles, you really wouldn't know what it was. It really takes a step back, or it takes all these people talking together to realize what is this thing? How is this fishery doing? So when possible, use multiple clues from multiple data sources. Here's some example indicators and reference points from the AFAM toolkit. So we'll go over all these in detail a little bit later on. I just want to highlight that these come from three major data sources. Some sort of catch reporting system, which monitors catch or catch arena effort, a length composition survey, which measures the lengths of individual fish, and an underwater visual survey, which counts fish underwater. There's two main steps for Step 3. The first is to select your performance indicators, and then for each indicator, you select reference points. In Step 3A, selecting performance indicators, indicators will depend on what data you have, the target species, and your assessment and management tier. Certain indicators you'll need certain data. Now, when possible, you want to select multiple indicators from independent data streams, but generally don't use more than 3. If you use more than 3, they can be really hard to interpret together. So for example, if you have catch, length, and underwater visual survey data, pick an indicator from each data stream. Or if you have just one of those or two of those, that's okay too. Again, all indicators are associated with pros, cons, and caveats. None are perfect, but there's some detailed descriptions of each method in the guidance document, so you can better understand these. Now, once we've selected our performance indicators, we want to select reference points for each indicator. So for each indicator, we'll set a target reference point. This is where we want to go, and a limit reference point. This is what we want to avoid. There's a couple of different ways you can set reference points. These can be based on literature. So there are a lot of best practices in the literature about what a healthy and sustainable reference point looks like. You could also base it on your specific fishery. You could look at trends. For example, a perfectly acceptable reference point would be, I want catch to be increasing. You could also look at historical data. So for instance, a reference point could be the average catch over the last 5 years. If you feel the last 5 years has been a relatively stable and desirable fishery state, you might just want your reference point to be an average over the last 5 years. Now, as always, local knowledge should be used alongside biological knowledge in setting reference points. The AFAM Toolkit dashboard has a system for selecting performance indicators and reference points. Based on the data you upload and the assessment management tier you're in, it pre-populates a list of suitable indicators and standard best practice reference points. Now, after you've uploaded your data and answered a couple of questions, it only shows appropriate indicators as options. Something the dashboard does is pre-populates this for you, but you may want to check and make sure all the numbers look good for your fishery, and you can of course adjust these as desired. So here are the methods included in AFAM. We have 4 length-based methods that use length data, 2 catch and effort methods that use catch or CPUE data from a catch reporting system, and 2 methods that come from underwater visual survey data. So we're going to talk in detail a little bit about the theory of each of these methods. Now, before we start talking about the length methods, it's important to talk a little bit about common life history information for data-limited fisheries assessments. Now, in order to make sense of length data, we really need to understand a little bit about how fish populations work and what these length data mean relative to certain key life history features of the species. So we're going to talk about a couple of different concepts. The first is age to length conversion parameters using the von Bertalanffy growth equation. We're going to talk about length to weight conversion parameters. We're going to talk about the concept of maturity and also mortality. First, though, a little bit about measuring fish. There's multiple different ways to measure fish. You could think of the total length, the fork length, or a standard length. Now, different places and different fisheries might measure their fish slightly differently. Something that's important is that you always want to use the same type of measurement throughout the AFAM process. If you measure your fish in total length, then you want to make sure all of your life history parameters are in total length and that all of your data are in total length. So let's talk a little bit about some equations. So some of the most important parameters for data-limited assessments are age to length conversion parameters, which use the von Bertalanffy growth equation. Now, we don't need to dwell too much on this equation, but essentially there are 3 parameters that determine how long a fish will be for a given age. So as fish grow older, they grow longer, but only up to a certain point. So L infinity is the length of a theoretically infinitely old fish. K is the growth rate. And T naught is the theoretical age of a zero-length fish. Now, you don't need to get too hung up on the fact that you can't have a zero-length fish or a fish that's infinitely old, but these are just the important parameters to keep in mind when converting between fish age and fish length. There's also length to weight conversion parameters. So on this figure, on the x-axis we have length, and on the y-axis we have weight. So the length to weight conversion parameters help us convert between a length measurement and a weight measurement. They use this equation where weight is a function of length in terms of these 2 parameters, a and b. Let's talk a little bit about maturity. The M50 number is the length at which 50% of fish are mature. So just like people, fish don't all mature at exactly the same age, but typically they'll mature in a similar age bracket. So M50 is the length at which 50% of fish are mature, and M95 is the length at which 95% of the fish are mature. Typically, M50 can be found in the literature. M95 is also often found, but sometimes not. And if not, it can be used on a relationship to M50 or to L infinity, which we discussed before. Now, as you can imagine, when we start thinking about our data-limited assessments, it's really important to know when fish are becoming mature. And if we're catching a lot of fish that are below this length, we're catching them before they've had a chance to reproduce, which is not a sustainable situation. Final important concept is mortality. So mortality is how quickly fish are dying. Now, total mortality, which we denote as Z, is a combination of two things. It's a combination of natural mortality, which is all the natural things that happen to fish. They die of old age, they die of predation, and so forth. Fishing mortality is what we as humans influence on the population. So total mortality is the sum of these two things. So the important life history parameter here is natural mortality. Now, this can often come from literature, but there are also relationships that can be used if you can't find this in the literature that relate it to M50 or K from the von Bertalanffy growth equation. And there's a link to a really nice online tool. Now, so you might need a lot of these parameters to run your data-limited stock assessments. So something we've done with the AFAM toolkit is built a species life history database. This has a database of over 160 species that are commonly found in the Philippines, Indonesia, and Mozambique. Now, if you happen to have one of these species at your site, the AFAM toolkit comes preloaded with all of the information necessary to run all of the assessment techniques for that species. And this will automatically populate when you use the dashboard. Now, if one of your species isn't in here, you may have to find these parameters on your own. And you can do that through a couple of sources. There's a great website called FishBase that has a lot of life history parameters for many, many species around the globe. If you can't find it there, it can often be found in scientific literature. You can look on Google, or even better through Google Scholar, to find papers that talk about life history studies. There's also tools for estimating natural mortality online. So now that I've given you a quick primer on life history information, let's dig into how we actually use this life history information and our actual data to say something about our fishery. So we're going to walk through each of the assessment methods included in the toolkit. The first one is fishing mortality from average length, also known as LBAR. The two main inputs for this assessment method are length data from individual length measurements and life history information. Specifically, we have some parameters from the von Bertalanffy growth equation and also natural mortality. As an output, we'll get an estimate of fishing mortality, or F, and also a ratio of fishing mortality to natural mortality, F over N. And this is a really powerful indicator for understanding how well the fishery is doing. If this number is about 1, you're probably in a pretty sustainable situation. If this number is higher than 1, you're probably fishing a little too hard. So here's a little bit of background and theory behind how the LBAR method works. As fishing pressure increases, larger fish disappear, and the average length, or LBAR, decreases. So here we've got 3 length frequency histograms for 3 different fishing pressures. So length frequency histogram shows on the y-axis different lengths, and on the x-axis different lengths, and on the y-axis the frequency of these different lengths. In the upper left we see an unexploited population, which as you can see has a lot of fish that are pretty big. As we move to these other figures, to the middle and the bottom right, we can see that as the fishing pressure increases, more and more large fish disappear and we're left with more and more small fish. And what is happening here is that average length in these populations is decreasing. Now to use this information, we can use an equation that converts some of our life history parameters and our length frequency histogram to get total mortality z in this equation in the bottom left. And once we know total mortality, and if we know natural mortality, which is the life history parameter, we can calculate fishing mortality using this simple equation f equals z minus m. The way we do this is look at a couple lengths in relationship to our data. We first look at L infinity, which is the life history parameter, based on the asymptotic length of an infinitely old fish. We next look at LC, which is actually a parameter we get straight from our data. This is length at full selectivity, which is the highest point in our histogram. We then calculate L bar, which is the weighted mean between LC and L infinity. Using all of this together in this equation, we can calculate our z and then our f. Now, something I'd like to say now at this point is that as we go through all of this theory and I show you these equations, it's great that you keep this in mind, but you don't have to remember all of this. AFAM calculates all of this for you, so you don't have to go through and do all these calculations manually. So what does this assessment method tell us? We get an estimate of fishing mortality, and this gives us finally an estimate of fishing mortality relative to natural mortality. How does this information inform management? So, stakeholders set a target reference point f over m. A typical rule of thumb is that about 1 is a very sustainable target. We then compare our target f over m with the f over m from assessment and adjust our fisheries management controls as necessary. So if our f over m is a little bit higher than 1, we might want to make things a bit restrictive so we can bring things back down to 1. I'm next going to go over an alternative way to calculate fishing mortality from a method called catch curve. This uses very similar data as the previous method, but with just a couple of more life history parameters. Very similarly, it's used to calculate fishing mortality, or F, and the ratio of fishing mortality to natural mortality. So here's our length frequency histogram again of our data of our fishery, and these are our fish caught by our fishery. In this case, we're first going to convert all of our length data to age data, and this is done using the von Bertalanffy growth equation. And so now we have an age histogram, and so we have a number of fish at different ages. We then take the natural log of our histogram to transform the data points. This is basically a math trick to turn this into a line. We can then fit a linear regression to these points, and the slope is the negative of total mortality. And so this shows how many fish are dying each year as they progress from one age to the next. In this particular age, we get that the total mortality is 0.73, and then our fishing mortality, just like before, is calculated as total mortality minus natural mortality. Now again, I'm pointing out these equations and this theory just so you have a bit of background, but the AFAM toolkit will calculate all of this for you. Very similarly to the L-bar method, we'll get an estimate of fishing mortality and a ratio f over m. We'll compare this to a stakeholder set target reference point. A rule of thumb here is to set this to 1, and then we'll adjust fishery management controls based on how far apart they are. Moving on to another length-based method, let's talk about spawning potential ratio, or SPR. This has very similar data requirements as the others, but again it has a couple more life history parameters. The output of this method is an estimate of the spawning potential ratio of your fishery. Spawning potential ratio is a measure of egg production relative to a theoretical unfished population. Now in this figure on the left, we've got two length histograms. The gray one is a theoretical unfished population. and we can create this histogram using all of the life history parameters that were shown on the previous slide. The red histogram is the observed size frequency, so these are the actual fish being caught. SPR is simply the area of the red curve under the area of the gray curve. Now you can see here, you could imagine that the gray curve has a lot more larger fish and can produce a lot more eggs relative to the red curve. And so SPR simply gives you a sense of what this ratio is. So why are the number of eggs so important? Well, here's a little bit of a concept shown with human population. So if we look at this middle row here, if we have 2 children per couple, we're at a replacement level, and the population will remain stable if two children keep coming out of every couple. If we have greater than 2 children per couple, we'll have population growth. And if we have less than 2 children per couple, we'll have population decline. The exact same thing happens in fisheries. We can either have a stable population, a growing population, or a declining population. And this is all about how many eggs are being produced and how many of those eggs turn into fish. So what this method gives us is an estimate of spawning potential ratio. Typically, a good rule of thumb is to set this at about 0.4. And so in this method, we'll compare our target with the SPR we actually measure in our population, and then adjust the fishery management controls as appropriate. If our SPR is greater than 0.4, this is a good thing. This means we have a pretty high spawning potential ratio, and things are really good. If we're below SPR, we might want to make the fishery a little bit more restrictive so that we can bring it back up to 0.4. The final length-based assessment method is called the FROSI sustainability indicators. Similar to the other methods, this takes as inputs length frequency data and a number of life history parameters. Now here we get a number of outputs. We get the percentage of mature fish in the catch. We get the percentage of fish caught within 10% of an optimum length, which is the length that yields maximum sustainable yield. We get the percentage of mega spawners in the catch. Now these are the really big fish that are producing a lot of eggs. And then using these 3 pieces of information, we determine if spawning biomass is above a sustainable reference point. Now the nice thing about this particular indicator is that it's very intuitive. The percentage of mature fish in the catch is an incredibly intuitive indicator that is very easy to explain to stakeholders and fishermen. It's easy to understand that if you have a whole lot of immature fish in the catch that don't get a chance to reproduce and make new fish, that the population will likely decline. So here's the concept. 3 general ideas behind a sustainable fishery are to first, let them spawn. So allow fish to get to a mature length. The indicator here is the percentage of mature fish in the catch. Typically we want this to be over 90%. The second idea is to let them grow. And so here, the indicator is the percentage of fish caught within 10% of an optimal length. This is a length that yields maximum yield. Typically we want this to be about 100%. Finally, let the mega spawners live. These mega spawners are the big fish that produce a lot of eggs. So the indicator is the percentage of mega spawners in the catch. Typically, we want this to be about 10%. Now, using these 3 pieces of information combined, we can use a nice decision tree to determine whether or not spawning biomass is sustainable. You don't have to pay too much attention to this decision tree because, again, all of this is calculated automatically for you in the AFAM Toolkit dashboard. So from this method, we get the percentage of mature fish, the percentage of fish within a range from an optimal length, percentage of mega spawners, and whether or not the spawning biomass is sustainable. And based on this, we can adjust our management controls to make sure that either the spawning biomass becomes more sustainable or that we catch more mature fish. Let's switch gears a little bit to two of the indicators that come from our catch monitoring system, which are trends in catch and trends in CPUE. The inputs for trends in catch are simply a time series of catch data, so we don't use any life history information for these new indicators. The output is a trend in catch, whether it's going up, down, or stable. In this figure here, you can see the catch is going down over time. What this tells us, whether catch is increasing, decreasing, or stable. How does this inform management? Well, we can adjust our management controls to hopefully combat whatever trend we're seeing that seems undesirable. Or we can simply let things stay if things are getting better or stabilizing. Trends in CPUE is very similar. As inputs, we look at a time series of catch pre and effort data. As outputs, we look at trends in whether it's going up, down, or stable. So again, we can use this information to adjust fisheries management controls to hopefully keep things either stable or increasing. Finally, let's shift gears to the two indicators that come from underwater visual survey data. So this comes from underwater surveys, which could be done by scuba or snorkeling. And as inputs, we take the biomass that are both inside and outside of a no-take zone, and also the total biomass across all species. So this first indicator, the fish to unfished biomass ratio, is an indicator across all species at the ecosystem level. And the output is a ratio of fished biomass relative to unfished biomass. Now, of course, this makes the assumption that the no-take zone is unfished and represents an unfished population. This assumes there's good enforcement and good compliance, and that the no-take zone has been there for a while. If that's not the case, this might not be an appropriate indicator to use. Now, what's the theory behind the fish to unfished biomass ratio? So the general theory is that as this ratio decreases, the ecosystem is more likely to go into a shift, an ecosystem state change. So on the x-axis, we have the fish to unfished biomass ratio, and on the y-axis, we have the likelihood of ecosystem state change. So if this ratio is very high, it's likely that we have a pretty healthy ecosystem and that things are doing okay. That's about greater than 0.5. If it's less than 0.5, it's likely that the ecosystem recovery is potentially possible, but a state change is a likelihood if we don't do anything. If this number goes below 0.25, it shows that an ecosystem state change is happening. This means that likely corals are going to go down and algae is going to go up, and the ecosystem is really going to fundamentally shift. And so knowing this number is a very good indicator of general ecosystem health. So this tells us the fish to unfished biomass ratio across all species and allows us to adjust management controls accordingly. So if this number is high, it might mean that things are pretty good and we don't need to do anything. If this number is low, we might need to take action. Finally, we looked at the fish to unfished density ratio. So this uses density inside and outside the no-take zone, but only for the target species. So only for species that we're actively fishing and looking to manage. And so this number, instead of the previous one, is individuals per hectare. And the output is the ratio of the fish density relative to unfished density of our target species. So this tells us a ratio, which again, a higher number is good, where a lower number is bad. And we can use this to inform management to adjust our controls accordingly. So now that you have a sense of the indicators included in the toolkit and a little bit about the theory behind them, I encourage you to look through the instructions and references for step 3. Then I encourage you to look at your fishery and record your choices and notes for your AFAM Toolkit worksheet. And then finally, go through this process on the AFAM Toolkit dashboard. Thank you very much, and we look forward to seeing you back for the next session.